All right. So let's take a look. I'll notice some corrections that might have been confusing, and I'll, in fact, I'm going to go through those right now. When we get to number 7, the wording for 7 should have been, which of the following arrangements is in order of decreasing size? Notice that all of these carets facing right, so it should be in order of decreasing size. That might have confused some folks. Another one on page 4, this will be faster. 17. I don't know how that thing got in there, but it's not related to any of the questions before or after it. So I needed to X that out. And I think, and then 52, which is on page 11. Here, instead of select the lattice energy from the following data, calculate the lattice energy from the following data. And you select the lattice energy from the multiple choice, A through E. I believe that's takes care of the errors that I noticed. Okay, so let's go back to the top. And I've got some marked off here that I want to cover. In fact, quite a few of them. I just hope I have enough time to get to all of them, because each one has its own bearing on topics. Okay, number 1. The force between two bodies having identical electric charges is, and our choices are, is a force of repulsion. A is true. Okay, A is a true statement. Let's see if they're any better, because the rule is in a multiple choice test, or at least in my multiple choice tests, if you can't find the answer that you think is exact, then pick the best one. A is true. B is a force of repulsion. Now that far, up to that point, is true. Let's see what the rest of the statement says. Is a force of repulsion if the charges are negative, and one of attraction if they're positive. Okay, that's kind of ludicrous. If the charges are of the same sign, they're always repulsive. So B is false. Of course, you may reason that if time is short, then the first one you come to that fits the conditions should be the right one. C increases as the bodies are moved further apart. Actually, it decreases as the bodies are moved further apart. So the force of repulsion is dependent upon both the sign of the charge, actually the magnitude of the charge as well, and the distance between them. D is independent of the distance between them. I just said it was dependent upon, so that one's false also. And then is directly proportional to the distance between them. That's also false. This is Coulomb's law. That's a different F from these. These are true or false. This is force. So the force between two charges is equal to the magnitude and the sign of the charges. And then there's a proportionality constant. I don't remember what the representation is, but it's a constant. It's Coulomb's constant. And then the distance between them squared. So this is a common phenomenon in physics, and it has to do, and it's to cover them all. It's called the reverse square law, the inverse square law. Excuse me, the inverse square law. It has to do with forces between objects. This is for Coulomb, for charges. It works for gravitational forces in Newton's universal law of gravitation. You'll find that term in there also. And also for the intensity of radiation decreases as the square of the distance from the source. Okay, so that's one. And the answer to one is A, of course. Number two, atoms having equal or nearly equal electronegativities are expected to form what? All right, we're talking about bonds. If they have equal or really, really close electronegativities, but they still form a bond, what kind of bond would you expect? Well, when the electronegativities are very close, nobody wins when they're fighting over electrons. So the only option they have is to share electrons, and that means covalent. Covalent bonding. But there's even more than that. If they're nearly equal in electronegativities, the bonding is not just covalent, but it's nonpolar covalent. Okay? And the best answer for that one is C, nonpolar covalent bonds. Now, I didn't check. I assume everybody can see this. I haven't heard any complaints, so I'm going to go ahead on. Since it's shared, it'll be recorded. Okay, for 3, I believe, yeah, I'm going to do the whole first page. For these elements, cesium, fluorine, and chlorine, the order of increasing electronegativity is. So the last one has the highest, the first one has the least, and then there's one in the middle. So the easiest way to deal with this one is to use the periodic trends. If we have cesium, fluorine, and chlorine, then we just look at our periodic table and we see where are they in relation to one another. Cesium is way down here, right? So it should have the lowest electronegativity. Remember, lower left, upper right. And then we get to fluorine and chlorine. We're actually in a group. So the electronegativity increases as you go up in a group. So that means fluorine should have a higher one than chlorine. And both of them on the far right-hand side of the table, they should both be greater than cesium. So it should, in order of increasing electronegativity, it should be fluorine first, then chlorine, then cesium, which is, increasing, I'm sorry. I was thinking decreasing. So it should be cesium less than chlorine, less than fluorine. There you go. So that makes the answer B. Okay. Let's see what 4 has to say. The electron pair in a carbon-fluorine bond could be considered, okay, what choices do we have? Okay, so choice A says the electron pair in that bond And it could be bound, and probably is, to some other things. Fluorine's probably just that single bond. But we're only concerned about that one bond between carbon and fluorine. So what about the electron pair? A says it closer to carbon because carbon has a larger radius and thus exerts greater control. But that's just ludicrous. The thing that determines the residence time of an electron pair and a bond is electronegativities. So fluorine has a higher electronegativity than carbon. They're going to be spending, if we draw a density shell, the electron pair is going to be spending most of its time near fluorine. So A can't be it. B, the electron pair is closer to fluorine because fluorine has a higher electronegativity than carbon. That is true. And you can determine that from the periodic table itself. You just look at where they are. Carbon is here. Fluorine is to the right of carbon, has a higher electronegativity. Let's see, I heard somebody show up. Let me record who it is. Or did somebody disappear? No, somebody showed up. One, two, three, four, five, six, seven, 8. Why am I cutting? Okay. Sheets. Okay. Simon. Galen. Jackie, Jeannie. Ah, there we go. Okay. So now I'm only missing Justice and Lacey. Okay, so we found the right answer. In the interest of time, I'm going to leave it there. The answer for 4 is B. Okay, the last one on this page is 5. Which of the following molecules has no dipole moment? So first of all, what's a dipole moment? A dipole moment is a way to express the unequal distribution of electron density in a bond and by inference later in the molecule. So bonds can have dipole moments, whole molecules can have dipole moments. So, and we represent that by an arrow. Right? The arrow points toward the maximum electron density. And then the plus end of the arrow is showing where the deficiency of electron density is. And in a bond, we may represent that as that delta with a plus or a minus sign to show us a slight negative charge or a slight positive charge. Okay, in this case, we're looking for molecular dipole moment. So what do we need to know to answer that question? You know, 2 things. One is, does it have polar bonds? Do the bonds show dipole moment? And second, if there are dipole moments in the bonds, what is the geometry of the molecule? Okay. So the first one is carbon dioxide, right? So how do you know? First of all, carbon's in the center, oxygen's on the outer rim. So you would need to draw your Lewis dot structure first, with carbon in the middle and oxygen's out here. So we have how many valence electrons for carbon? Right, we have 4. Each oxygen has 6, which is 12, which means 16 electrons. So then you put a bond between them. So that's 4 electrons used. That means we have 12 electrons left over. So we got to put them in there someplace. So 2, 4, 6, 8, 10, 12. Okay, all used up. And then what do? You try to satisfy the octet, if at all possible. And in this case, carbon doesn't have an octet. Both oxygens do. So we take a pair from this side and make a double bond. Right? We take a pair from this side and make another bond. Now we have a valid Lewis dot structure. Now, how do we know it's this one and not that one? Formal charge tells you. So what's the formal charge on carbon? Well, it starts out with 4, right? 4 electrons as the free atom. How many is it assigned in the molecule? Well, in this one, it's got 1, 2, 3, 4. Half of a bond goes to carbon. So that means its formal charge is 0. How about the formal charge for oxygen? Well, oxygen has 6, right? How many does it have in this molecule? 1, 2, 3, 4, 5, 6. So all the atoms in this representation are formal charge 0. In this case, you've got carbon still has 0, because it's 1, 2, 3, 4. This oxygen has 1, 2, 3, 4, 5, which means it's plus 1. And this one has 2, 4, 6, 7, minus 1. So which one do you choose? Choose the one with the formal charges for the most atoms that are close to 0. So that's why that one is the correct one. Now we have to look at, well, let's get rid of some of the junk. Okay. There we go. Now, there's our molecule. Does it have polar bonds? The answer is yes, because oxygen is much more polar than carbon. So it'll have a dipole moment this way for that bond, and this way for that bond. But is that the correct geometry for that molecule? Now you got to say, all right, according to the VSEPR model, the central atom has 2 groups, which means automatically linear. So this is the correct representation. 180-degree bond. That's a linear molecule with equal polarity pulling in both directions. They cancel one another out. So this one is nonpolar molecule. It has no dipole. All right. So that answers the question. That's why the answer is A. But while we're here, let's look at the others, right? How about ammonia? Okay, let's draw the Lewis dot structure for ammonia. Nitrogen has 5 valence electrons because it's 5 steps over from the left in its period. Then we have 3 extra ones from hydrogen, 1 each. That means we have 8 electrons. Right? So we put nitrogen, and then we bond 3 hydrogens to it. 2, 4, 6 from 8 is 2 electrons left over. Where do they go? They can't go on hydrogen, work from the outside in, so they have to go on nitrogen. All right, so now we have a valid Lewis dot structure, and there are no other alternatives. That's the only one possible. So what does the VSEPR say about 4 electron groups? First, you do the electronic structure. So the electronic structure here is 1, 2, 3, 4 groups, means tetrahedron. Okay. Like that, with nitrogen in the middle, hydrogen there, hydrogen there, hydrogen there, lone pair there, and nitrogen in the middle. So that's your electronic structure, is tetrahedron. But the molecular structure is the one we're aiming for. First of all, do we have a dipole moment here? Oh, well, yes, because nitrogen is even farther to the right than carbon. And against hydrogen, we have like that, and like that. And then, of course, this gives it an extra boost toward the lone pair. So they're all aiming this way and that way. And because we don't have a balance here with another hydrogen, then we have a dipole moment for the molecule. But also you have the molecular structure, which in this case, what's left over? A trigonal pyramid, which means that, yes, the dipole moments for the bonds are all unbalanced. So the dipole moment here is like that. Okay, how about water? We've done water several times before, and it's a bent molecule. With the dipole moment this way for that bond, and this way for that bond, plus the 2 unbound lone pairs, and all together, they give you a dipole moment that way toward the oxygen. Okay, so we've already said the answer to this one is A. And D says all of them have no dipole moment, which is false. None of them have no dipole moment is E, which is also false. So I took a little extra time on 5 because it also incorporated determining Lewis structure, determining dipole moments for bonds, and then using VSEPR to find the electronic and then molecular structure. So that's why we spent a whole lot of time on 5, covering a lot of ground with just one problem. Okay, let's see. Do I have 6 checked off? Yeah, in fact, I got the whole next page. So I need to move along in the interest of time, of course. Okay. So which one of these has the smallest radius? All right. This one could be a stumper. Okay, we're looking at potassium, chlorine, rubidium, and sulfur, and then argon. Okay, how do you compare the radii of these elements? We're not given any quantitative data, so we have to work from periodic trends. All right, so now if we're looking at just the ground state atoms, then the periodic trend for decreasing radius is the same as the electronegativities, lower left to upper right. But we're looking at ions, so we need some other way to compare them. And as it turns out, some of these are isoelectronic. which means something, of course. It means that they each have the same electronic structure. But let's be sure that we have that we're able to compare them that way first. Okay, if we start with argon, it's ground state, right? So argon is going to be 1s2, 2s2, 2p6, 3s2, and 3p6. Sulfur has 2 extra electrons to the left of argon. So sulfur would normally be 2 electrons short. But now, with those extra 2 electrons, they go into the 3p orbital and they make it look exactly like argon. Just like that. So the sulfide ion is isoelectronic with argon. Where's rubidium? Well, rubidium is, let's see, rubidium is down here in the 5th period, and it's lost an electron, so it actually looks like krypton. So that means it would be argon plus 5s2, 4d10, 5p6. Okay. Chlorine is only 1 to the left of argon, right? So when we add an electron, now it looks like argon. And you can check that out on your periodic table. That's what's good about the table. If you add an electron to chlorine from here, shifts it over to look like argon. Right? So these two look like argon. Of course, argon looks like itself. How about potassium? Well, potassium has lost an electron. And when potassium loses an electron, it loses all of its period 4 character. It lost the electron that it had in 4s orbital. So now it only has 3s and 3p orbital, and they're full. It makes it look like argon. Okay? So this one, that one, and that one are isoelectronic with argon. Rubidium is bigger than anybody because it exceeds argon by d orbitals and, well, let's see, yeah, by both 5 and d orbitals. It's beyond 3. So the rubidium plus is the biggest one in this group. Its electrons are way out here. So let me go back to the problem. Which has the smallest radius? All right, so it can't be rubidium, right? Now, what about the others? If they're all isoelectronic, then what you want is to know how many protons are there. They might have the same number of electrons, but they still have different number of protons. So let's look at argon has 18. Sulfur has 16. Rubidium has 37. We threw that one out already. Yeah. 37. Chlorine has 17. And potassium has 19. Since we're not dealing with rubidium because it's got all these extra electrons way out there, right? So this is the dominant effect for rubidium. It's too big. So for the isoelectronics, we look for the one with the largest number of protons. because they're going to draw the electron density down with that extra positive charge. So the largest positive charge is potassium. This potassium ion has the strongest draw on the electrons that it has available, which are the same number as the rest of them in the same orbitals. So that's why the potassium ion is the smallest radius in this group. Now, I know that took a long time to explain, but I didn't think it would really make sense if I just blasted through it. We needed to approach it logically. I get the feeling I'm still going to be talking when, when the class bell rings, because I want to get through all of these problems. They're each important in their own way. We might be able to skip 7 because it works on the same principle as 6. We look for the isoelectronics, and we order them based on the number of protons. And if there are any that are greater, have more electrons in outer regions, then they were going to exceed the other isoelectronics. And that's why the largest size is the sulfide ion here, this B. Let's see, where's my pointer? Okay, it doesn't have a nice pointer. And so forth and so on. I think the explanation in the work problems is adequate for this. Once you realize that the wording is wrong, it should be decreasing size, because it goes from largest on the left to smallest on the right. So I'm going to leave 7 alone. Let's look at number 8. In the reaction between magnesium and sulfur, the magnesium atom what? Well, let's see what the choices are. That dictates the approach to the solution. A's become anions, B become cations, become part of polyatomic ions, share electrons, crystallize. Okay, so we're going to have to approach these separately. So for A, we're starting with magnesium and sulfur. And they form, and they're both solids. They form this compound. How do we know they form that compound? Well, first of all, magnesium's a metal, sulfur's a nonmetal, which automatically means ionic bonding, especially since they're very far apart. Magnesium on the far left side of the periodic table, sulfur on the far right side. So you know that their electronegativities are far enough apart that they're going to form ionic bonds. So that implies transfer of electrons. Okay, so in order for that to happen, in fact, we don't even need to know the exact formula. We just need to know metal, nonmetal. So what happens to the electrons? Well, typically, metals like to lose electrons, and nonmetals like to gain electrons. Now, why is that? One of the driving forces is it helps them look like noble gas. So magnesium, if it loses 2 electrons, which is a lot easier than gaining 6, then we back up 2 and we end up at neon. Magnesium now looks like neon if it loses 2 electrons. Sulfur, on the other hand, if it gains those 2 electrons, it looks like argon. So both are happy with the least amount of effort. But what does that make each one? Well, the magnesium atoms, which is part of this problem, says what? Becomes anions or becomes cations? Well, a cation is a positive ion. So if magnesium loses electrons, it becomes cation. That's why the answer is B. Does it become a polyatomic ion? Actually, no. All polyatomic ions are covalently bound. They do have a charge, but within the ion, all of the bonds are covalent. For example, the ammonium ion is a polyatomic ion. It's a group of atoms that behaves like a single unit, cation. Each of these hydrogens surrounds the nitrogen in a tetrahedral form. And the entire group has a positive charge. All right, that gives nitrogen an octet, 2, 4, 6, 8, but it also has the charge. Now we could do the Lewis dot structure here if we had time. But the point is, all polyatomic ions are covalently bound internal to the ion. Share electrons with sulfur? No. That would be a covalent bond, and metal and nonmetals do not form covalent bonds. There are winners and losers. Not to say that they're both not happy with the situation, but some lose electrons. The metals lose electrons, and the nonmetals gain electrons. Crystallize in the reaction between magnesium and the magnesium atoms do not crystallize on their own. So it's a trick in the wording. If we said the magnesium sulfide crystallizes, yes, that would be true, because this is all ionic compounds form crystalline solids. But the magnesium atoms themselves do not crystallize. They become ions, cations in particular. Okay, number 9. Let's see. Choose the molecule with the strongest bond. All right. So number 9. A, B, C, D, and E. All the same. And then we have F2, Cl2, Br2, and I2. Okay. Now the trick to this one, let's see. I want to be consistent with my explanation. If I find a better one, I'll give it to you. Okay. If we just say, since all of these bonds are covalent, that's true. And they're nonpolar. Why? Because both atoms have identical electronegativities to one another. So they're going to be covalent, they're going to be nonpolar. So then we have to shift to thinking about, well, we know that the stronger covalent bonds are the ones that bring the atoms closer together. So we would say this one is the weakest. The iodine bond is the weakest. Then bromine is stronger. Chlorine is stronger because we're moving up the periodic table. That means that the atoms are getting smaller. which means that brings them, they can get closer together for their bonds. And then, so we get a stronger bond as we go up. The problem arises when you get to fluorine. When you start pushing, when these fluorine atoms get that close together, then you start experiencing repulsive forces from the nuclei, because fluorine is going to have 9 protons. And when you get them that close together, then you start experiencing repulsive forces. So the trend breaks down from chlorine to fluorine. That's why the answer, the strongest bond, the greatest bond energy is between the 2 chlorines rather than the 2 fluorines. Now, we don't have any, this problem doesn't give you any quantitative data to back that up. So that's why the logical approach is the best we've got to go on for this problem. But if we had the quantitative data, it would bear out the fact that chlorine, in fact, has the strongest bond of all of these diatomics. Okay, let's keep shifting over. Yeah, there we go. Let's see. Which of the following exhibits the greatest bond energy? Did I skip one? Yeah, I did the wrong one. The bond energy, sorry. Actually, 9 and 10 go hand in hand. When we say which one has the strongest bond, which one exhibits the greatest bond energy, those are 2 ways of saying the same thing. So I think that was the point for putting 9 and 10 in there together, as to help you recognize that with those statements, we're saying the same thing. The strongest bond is sort of a qualitative approach, but the bond to energy actually requires expression of kilojoules per mole input in order to break the bond. So 9, in effect, is a qualitative expression. 10 is a quantitative expression. Okay. Number 11. Let's see if we've got time to do this one. Draw the Lewis structures for the molecules below and use them to answer the following questions. 11 says, which of the molecules obeys the octet rule? All right. As it turns out, only one of them obeys the octet rule. I think we need to move ahead, actually. So let me keep tally of the ones I skipped. 11. And if there's time, I'll come back to it. 12, because we've already discussed these topics earlier, and you just recognize that you don't have to make an octet if you don't have the electrons for it, or you can exceed the octet if you're forced to put lone pairs on the central atom, is usually the case. And those central atoms which exceed the octet are going to come from the third fourth, excuse me, from the 4th period on down. Why? Because they have access to d orbitals. And d orbitals is where those lone pairs go in this particular model. Okay, so let's move on down to, yeah, let's do 13. Okay, I heard some noise. Let me see. Did I get somebody? 8? No, I didn't get anybody extra. Okay, so let's carry on with 13. How many electrons must be shown as bonding or non-bonding electrons in the Lewis structure with their skeleton listed below? So we've got carbon, 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 carbon. 1, 2, 3, 4. We're just labeling which carbons there are because there may be questions saying, what about carbon 3? You know, and that's why that subscript is there. It doesn't mean that there are 3 carbons there. So we're violating that, the 4-position rule. Then we have hydrogens and that oxygen. And another one here. Okay. Okay, this question is really simple to answer. How many electrons must be shown as bonding or non-bonding electrons in the Lewis structure? So for that, all you do is count up the number of valence electrons. Right? Hydrogens, 1 each. 1, 2, 3, 4, 5, 6. Carbons are 4 each. 1, 2, 3, 4 times 4 is 16. And oxygen is 6. Right? So it should be 28 electrons, which makes the answer D. But then on the next page, we're using the same model and we're asking a different question. How many electrons are shared between carbons 2 and 3? Here. We only show 1 bond there. But notice, if you just take that 1 bond, that these carbons do not have an octet. So what you would need to do is place the electrons after you subtract the bonds. So we've got a single bond here, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, so we've got 8 electrons that we need to deal with. There's 6, work from the outside in. This carbon's already got an octet. That one doesn't have an octet yet. If we put 2 electrons there, then that gives it an octet, but these guys are starved. So what we do is we make the octet here by transferring to a double bond there, and we put the other pair shifted over 1 carbon. Now we can use those 2 to make a double bond there. So now we have an octet. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. We're good. So now the number of bonding pairs we have in here, we have 2 bonding pairs, which means 4 electrons. So that's why the answer is C. This one might be a little confusing because you have to know that by working this direction with your lone pairs, that you're going to end up still starving these 2 central ones. So that's why that lone pair shifts over here and makes the double bond, because you've already got a pair here that you can make a double bond with. And then the verification for that is the formal charge. If we did it the other way over here, well, it wouldn't work because we wouldn't be able to form a octet for either one of those. And the formal charge would tell you that. So the formal charge would be way away from 0 for all of these. Well, for most of them, at least those over here. Oxygen would be way off. No, this carbon would be way off. and these carbons would be way off. But with this, in fact, I think I'm correct in saying that all of these have a formal charge of 0. So that would give you the best structure. Okay, I actually did 13 and 14 there. Let's see. We answered 15 with when we drew the structures. There are no double bonds in ammonia. There are no double bonds in water. The only double bonds there are in carbon dioxide. In fact, there's a double bond on both sides of the carbon. The Lewis structure for ICl2 minus, how many lone pair electrons are around the central iodine atom? I think we can knock this one out pretty quick. So there we go. Excuse me. With a 2. Count up the valence electrons plus any additional electrons, or if it's a positive, you have to subtract 1. Right? So don't forget the sign when you're adding up electrons. So iodine is 7, chlorine is 7. So that's 3 times 7 is 21, plus 1 is 22. Iodine's going to be in the middle. Okay. And then we've got, that means minus 4, which is 18 electrons. 2, 4, 6, 2, 4, 6, 8, 10, 12. Minus 12, which is 6 electrons. So now we're going to have 2, 4, 6. So we should have 3 pair on the central atom. That's why D is the answer. Right? And we have exceeded the octet. 2, 4, 6, 8, 10. Iodine has exceeded. And that's okay for iodine because it's in the 5th period, which means it has access to 4D orbitals. There's plenty of room for the excess. Okay, let's see. I'll keep up with my hard copy here too. Now I'm going to, let's see, I'm not going to take the rest in sequence. I'm skipping over to 19. How many resonance structures can be drawn for the molecule O3? You know what O3 is? Ozone. Right? In the upper atmosphere, ozone is good. It absorbs ultraviolet radiation, protects us on the surface. But on the surface of the Earth, ozone is bad because it's an extremely reactive molecule. And if you breathe it in, it damages lung tissue. So that's why the first laser printers were notorious for generating massive amounts of ozone. So what they did was they incorporated into the, well, they just added packs of activated charcoal inside, not just to absorb moisture, but to absorb ozone as it was produced. And then later designs for laser printers came within healthful standards. And now whenever they put those packs in there, they're just to absorb moisture. Ozone. Okay, this is 19. O3. So each oxygen has 6 electrons, valence electrons. 3 times 6 is 18. And since there are 3 of them, right, 2, 4, which is 14 electrons, work from the outside in, 2, 4, 6, 8, 2, 4, 6, 8, 10, 12, there. Okay. Oxygen does not have an octet yet. So how do we form an octet here? Well, we can take 2 off of this and make a double bond. Right? That's 2, 4, 6, 8. 2, 4, 6, 8, 2, 4, 6, 8. Right? So now we've got the octet satisfied, but notice that we could have put the double bond on the other side. Like that. Okay. Are there any other possibilities? Well, they have to be, in order to have resonance, the structures must be equivalent Lewis structures. And equivalence, what we mean by that is that the array of formal charges must be the same. It doesn't have to be the same on each oxygen, but if this one goes up, if we come down from here to here, and this one changes up, then this one has to go down. In other words, the balance has to be maintained in the formal charges. Excuse me. In fact, we'd have no other options. If we had taken this pair and made a double bond, that one would have exceeded the octet, and this one would have been depleted, so we couldn't do that. The double bond formation has to come from the outside. And those are the only two structures that are possible. So we only have two resonant structures for ozone. That's why the answer is B. Okay, let's see. Which of the following, this is 20. Which of the following types of molecules always has a dipole moment? Okay. Always has a dipole. All right. Does linear molecule with two identical bonds? Linear with identical bonds. That's going to be nonpolar. If the bonds are linear and the bonds on either side are identical to one another, then they either approach or diverge from one another with equal magnitude and cancel one another out. So A can't be it. B, tetrahedral molecule, 4 identical bonds. The tetrahedral molecule with 4 identicals, all pulling in opposite directions or approaching each other from opposite directions, they cancel one another out also. So these are always nonpolar. How about C? Trigonal pyramid molecule with 3 identical bonds. So if the molecular structure is trigonal pyramid, why is it trigonal pyramid? Right? If we have an X there, and we have those bonds there, that's how you get a trigonal pyramid, but you only get a trigonal pyramid if there's a lone pair up here. Okay, so these can all be identical, right? But this lone pair gives the molecule a net dipole in that direction. So these can all be identical, like ammonia. That's not a good example because there's a difference between nitrogen and hydrogen in their dipole moments. But if we had I don't know of a good example, this is hypothetical anyway. If all these bonds are equal, then that lone pair, which is the only way you can get a trigonal pyramid, gives it a dipole moment every time. So since E says none has a dipole moment, then we can stop there. Trigonal planar molecules with 3 identical bonds. That's always going to be nonpolar. Well, not always, but it won't always be polar. It won't always have a dipole. Sometimes it will and sometimes it won't, depending on the bonds. Okay, so that's why C is the answer to 20. Okay. I'm going to skip 21 and 22 and 23 because I want to get to something before I run out of time. Okay, 25. Well, I'm gonna, yeah, let's do 25. Which of the following ionic compounds has the largest lattice energy? That is, the most stable ionic lattice is formed. Okay, so what do we need to know for this one? Barium oxide. Well, first of all, they all have to be ionic, so we better check that as we go. Yeah, metal, nonmetal, metal, nonmetal. Metal, nonmetal, yep. Metal, nonmetal, and metal, nonmetal. Okay, so they're all ionic. Let's look at the charges, right? So how do we determine the strength of a lattice? Well, of course, we have the definition of lattice energy, right? So we have the metal. We just say it's a single charge for now, but it could be a double charge. And this is a gas. And then a nonmetal gas comes together and forms a solid. And the energy that is given up when that happens is the lattice energy. Okay, so now what determines the strength of that bond between this position and that position? Two things. One is the size of the charge, right? Because Coulomb says the bigger the charge, the stronger the bond. But the other thing that determines the strength of that lattice energy is how close can they get to one another. If you have the same charge on both ions in two situations, and one of them has a smaller ion, it can get closer together, that forms a higher lattice energy, a stronger bond, right? So that's what we're looking for here. So let's say, what are the charges here? Barium and oxygen, that's 2 plus, 2 minus, 2 plus, 2 minus, right? Yep. Cesium, that's 1 plus and 1 minus, 1 plus, 1 minus, 2 plus, 2 minus. Okay. The 25, yeah, 25. What we can do is focus our attention on the 2 plus 2 minus ions, because they're going to meet the first condition for Coulomb, the strongest attractive forces between larger charges. So if we focus on this one, and this one, then what we need to do is look at the size of the ions, right? Which one has the smallest ions? Well, if we look at the cations, beryllium is the smallest one, right? You just look at where it is on the periodic table. It's at the top, right here, in the second group. So it's going to be the smallest 2+ ion. The rest of them are below it. So there's your smallest cation. How about the anions? Well, these two are equal, so that means this one wins over that one. But how about this one? Sulfur and oxygen. Sulfur anion is in the same group as oxygen, but it's larger, right? So that lets this one out, and this one is let out for that one. So B is your answer. That one will have the strongest lattice energy because of two things: the size of the charges and how close are they together. The size of the ions. The smaller ions mean stronger bonds. Okay, that was 25. Let's see. I'm going to skip 26 and go to 27 takes a little bit of calculation. I'm going to have to come back to that one. So let's make a special case for 27. Definitely come back to that one. Which of the following, 28. We're looking at the Lewis structure, and based on the Lewis structure, which of the following would probably not exist as a stable molecule? What we're looking for here is, first of all, octets. Do we have octets in each of these? Did I lose somebody? Yeah, I did. I lost somebody. Well, that's okay. It's time to go anyway. So if you have to go, fine. I'll just keep talking. So let's see. We have CH3OH, which is methanol, wood alcohol, the one you don't drink because it make you go blind. Then we have CH2O, which is formaldehyde. Then we have CH3O, which I don't know what that is. And C2H2, which is probably acetylene. And then we have C3H4. Okay, so which one, based on its Lewis structure, would probably not exist? So we can work our way down. This one is going to be, and this has to do with the way that we write organic molecules. When the carbon is followed by hydrogens, all of those hydrogens are bound to the carbon. And the carbon then is bound to the next atom. Right, so that's kind of something you haven't been introduced to yet. Okay. So that's going to have, that's its Lewis structure. It's perfectly good. That's fine. This one is going to be like that. That's formaldehyde. 1, 2, 3, 4, 1, 2, 3, 4. And you can go through the rules for Lewis structures and prove that I'm not lying to you. This one would be, let's see, 4 plus 6 is 10, plus 3 is 13. So 2, 4, 6, 8, 10, 12, 13. So even if we put 2 over here. Well, we don't need 2 over there. Carbon has an octet. But this oxygen has 2 things wrong with it. First of all, what's its formal charge? Carbon is 0. But oxygen starts off with 6 and ends up with 1, 2, 3, 4, 5, 6. Well, it ends up with it's 0. The problem is it's a free radical. Free radicals are not very common. It's not stable. An unpaired electron makes it unstable. And for 28, how did I get, let's see, get out here, 28. There we go, 28. I haven't been scrolling, have I? This is not a stable molecule because it forms a free radical. And I know we haven't defined free radical, but that's why I wanted to deal with this one, because that means this is an unstable molecule. Acetylene is like this. Oops, sorry. That's ethylene. Acetylene has 3. It's very stable. C3H4. So where do the hydrogens go? Well, let's see. 1, 2, 3, 4. Let's see. That's 12, 16. So we have 2, 4, 6, 8, 10, 12. From 16 is 4 electrons that we need to find a place for. We could put 2 there, and we could put 2 here. So it'd be 2, 4, 6, 8, 2, 4, 6, 8. But this one only has 2, so these 2 would go here. These 2 would go here. That's a stable molecule. We've met the octet. The problem with this one is the free radical. Okay. We did 28. All right, that's good. Let's see. I'm going to skip 29 also. And be sure, we haven't done any with calculations yet. All right, 35, 36, all the way down. Actually, the next 2 pages, actually 3 pages, we've got cases where you have to draw the Lewis dot structure, deduce the electronic structure from that using the VSEPR, and then answer the questions. It may ask you, is the molecule linear? Is the molecule what molecular structure? What electronic structure? What type of structure it may have? Let's see. Do we have those in here? Useful information, that's what I'm looking for. No. So you've got to know how to use the VSEPR model, and I'm gonna draw you the table. It's not any one particular one, but what you do is draw your Lewis structure, and then on the atom in question, if it's a simple atom, it's just the central atom. The central atom has these many electron groups. Why didn't I put group, only one group? God, if it's only got one group between the central atom and the other one, it's automatically linear. So we start at 2 groups. 3, 4, 5, 6 groups of electron, either bonds, and a group can be a single, a double, or triple bond, or lone pairs count independent, right? So you can have bonds on the central atom and the number of lone pairs around the central atom constitutes a group. So if you have 2 groups, the electronic structure is going to be linear. If you have 3 groups, it's going to be trigonal planar. Just think about geometric shapes. What puts the electrons in the bonds or in the lone pairs as far apart from each other as possible? Trigonal planar. It's an isosceles triangle, right, with 120 degrees between either the bond, in between the groups. 4 is tetrahedral. 5 is trigonal bipyramidal. And this is electronic. I remind you, this is only electronic first. You have to do the electronic first. And 6 is octahedral. Okay. Now the molecular is a little trickier, because you have to take into account the lone pairs and mask the lone pairs to see what molecular structure is left over. And when you get more complex down here, there are more choices. With linear, it can only be linear. There's no other possibility. Trigonal planar, if there's one lone pair, then it's bent. If there are 2 lone pairs, then it's linear, of course. Tetrahedral, if you have one lone pair, then it's trigonal pyramid. If it's 2 lone pairs, like water, then it's bent. Trigonal bipyramidal. If it's 1 lone pair, then you have a seesaw. If it's 2 lone pairs, and why do you have a seesaw? Because the best place for that lone pair is out here, which means you've got this as the base and there's your seesaw. But if you have 2 lone pairs, the best place for them is opposite one another. So in that case, you would have trigonal planar. Octahedral. This can get really complicated. Octahedral, if you have 1 lone pair, that lone pair is likely to be where? Okay, so you got 1, 2, 3, 4, 5, 6. Where would the lone pair be on this one? If we put it up here, it's 90 degrees away from these, 180 away from that one. If we put it out here, it's 90 degrees away from that one, but also 90 degrees away from that one. So the lone pair should be there, which means it's a square pyramid. With 1 lone pair. With 2 lone pairs, they should go opposite one another. And that means you would have a square planar. With 3, if you have 1, 2, 3, that would give you, I can't think of an example, so I'm not going to give you one of those. That covers most of everything. Now, if you're going to draw a Lewis structure and the molecule is an ion, so it would be like a polyatomic ion, or it would be an ion that was formed from one of these electronic structures. Don't forget to put brackets around it with the charge, because if you don't have the charge on the Lewis structure, that means that all those electrons have been accounted for in the structure only, and the net charge is 0, and it won't add up. So you need to have your molecule inside, and then the charge out here, if it happens to be a -1 or a plus or whatever it happens to be. Don't forget that. All right, before I finish, I want to do a problem with calculations. And the first one I come across, actually it's not the first one, but it's where I am, is number 50. Let's go down to 50. There it is. Use the bond energies given below to calculate the enthalpy change for the reaction. So you remember how to do that. This is 50. And the reaction is HCN plus 2H2 yields CH3NH2. CH3NH2. All right. So in order to do this calculation, you have to know what bonds are in the molecules. That means you've got to do Lewis structures for each one. Right. This is hydrogen cyanide. We did that one in class already. Okay. So let's see. That's 1, 2, 3. Actually, there's a lone pair out here. But for this calculation, the lone pairs don't matter. Hydrogen. That's it for hydrogen. This one is a little more difficult. You've got that. That's what this means. And then this is bound to that one, and it has 2 hydrogens. Okay. This is called an amine group, in case you're interested. Now this does not have an octet yet, so I'm pretty sure that it has a lone pair on the nitrogen. But those are the bonding sequences. Now, how do we calculate? Well, we take the number of each of these bonds on the reactant side and subtract the number of bonds on the product side, right? So you're going to have how many hydrogen carbon bonds? One of those. So there's one hydrogen carbon bond, which is 413 for this one. Then we have a carbon nitrogen triple bond, which is 891. Right? Then we have 2 hydrogen bonds, which would be 432 plus 2 times 432. Right? Then we subtract the summation of these bonds. There's only one of those out there. One molecule, so we only have to take into account one molecule. So we have 1, 2, 3 carbon hydrogen bonds. 413. And then we have one carbon-nitrogen single bond, 305. And then we have two nitrogen-hydrogen bonds, 391. There you go. That's the work. That's the hard work. Actually, the hard work is knowing this right here. So the answer should be minus 158. Which is B. All right. So that was 50. Let's see. I'm going to skip 51 and 52 and come back to them. Definitely 52, because I want to get to these last here, these short answer problems. All right. So 53 says, in spite of the large electronegativity differences between bonded atoms in beryllium chloride, despite the large electronegativity differences between the bonding atoms in beryllium chloride, it has no dipole, while sulfur chloride does have a dipole. Why is that? In order to explain dipoles, you need to know something about well, it's already told you that there's a large dipole moment in the bonds. So you need to know the structure. So beryllium chloride is going to have a structure which is, well, beryllium is has 2, 7 here, so that's 14, 16 electrons. All right, 2, 4, 12. Okay. 2, 4, 6, 8, 10, 12. Okay, so we're deficient. With the yeah, we're deficient with the octet for this beryllium. We can't. We're not going to make double bonds with beryllium. Why? Because beryllium only has is only here. There's beryllium. It's in the second period, right? Technically, it could have access to p orbitals. So we could do this, and now actually we can't do that. 1, 2, 3, 4, 5, 6. And technically we could. But either way, we end up with a linear structure. And a linear structure says no dipole moment. Sulfur has 6 electrons plus 14 is 20. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay. Notice any similarities between this and water? If we change that to oxygen and that to hydrogen, we still have 2 lone pairs on the central atom, which means tetrahedral, but it's a bent molecular structure and a dipole moment toward the sulfur because of the lone pairs. So this is a bent molecule, which means that its overall dipole is going to be toward the sulfur molecule. And that basic geometric difference between the beryllium chloride and the sulfur chloride explains why beryllium chloride is nonpolar, sulfur chloride is polar. Okay. Now we're going to do 54. Okay, if we're given ICl4 minus, the question is for A, what's the Lewis dot structure? All right, so we'll do that one. Give the shape of the molecule, indicate its polarity. We have to do the Lewis dot structure first anyhow. So we'll do it first, and then we'll answer B and C. So what's that? They're all halogens, so they have 7 valence electrons each. So it's 5 times 7 is 35, plus 1, 36 electrons. Okay, iodine's going to be in the center. Chlorine's around, like that. 2, 4, 6, 8. So that means 28 electrons. 2, 4, 6. If we do the same thing for each one, that's 4 times 6 is 24. 4 electrons left over. Right. They go on the central atom, and that means 0. Okay, so we're all zeroed out. What does that mean for the, I'm going to steal that one. There's your charge on that group. So that is the Lewis dot structure for iodine tetrachloride, ion. Now, what does that say about the electronic structure? 1, 2, 3, 4, 5, 6, octahedral. Right? But an octahedral with 2 lone pairs, the lone pairs go at the apexes of the octahedron, which means that the molecular structure is square planar, and all of these bonds are equivalent, which means they cancel one another out, and the molecule is nonpolar. Right? So B is square planar molecular structure, and C is nonpolar. All right. So we got that one out of the way. Now I can backtrack. Okay. So let's try, okay, 52. 52 is going to take some calculation. In fact, it's going to be hard to fit all the calculations on this tiny board. I'll do my best. All right. So if we're going to calculate, let me back up, excuse me. Back up, there's 52. Calculate the lattice energy for rubidium chloride from the following data. All right, let's see. There's another error. this, let's see. This should go over here. So let's put it over here. Hold on a second. I need some 0916. Let's see if this will work. Alt 0916. Nope, won't work. Let's see if I've got another one. I'm using my extended character set commands. That one didn't work. Let's see if I got another one to work with. No. Well, in that case, I only have left, and you can't see this because I haven't shared it, but I'm using the character map, and I'm looking for my delta. And it's right there. Okay, so all this is going on in the background and you can't see what I'm doing. So I hope this works. All right, there's my delta. And then I want H, F, and I need to make the F. There we go. Okay, so now I got that fixed, but I need to do something about this one. So let me draw a line through it there. And then I've got another one here that's a problem. Draw a line through it as well. EA, what does EA mean? Text. There we go. Okay. So, what do each one of these mean? That's one of the key things that we have to work out. This one defines the vaporization of the solid, rubidium solid to gas. That's how much energy it takes per mole. And this is in kilojoules per mole, just like the problem says, kilojoules per mole. Ionization energy. What does ionization energy for rubidium mean? Remember the definition of ionization energy. Let's see, where is it? Where is it? Where is it? We may not even need ionization energy. Yes, we will. Ionization energy is rubidium gas yields rubidium ion plus an electron. Right? So that's what that means, and that's the amount of energy that has to be put into it. So that's why it's a positive value. Ionization energy, the first ionization energy, i.e. 1, is 397.5 kilojoules. BE, what does BE stand for? BE is the, let's see. Oh, my mind's gone blank. I've lost it. Let me see if I can find an indicator somewhere for 52. Oh, bond energy. Bond energy for dichloride is how much energy do you get back when let's see, is that right? 226. Bond energy for dichlorine. Oh, okay. The bond energy for the gas going to like this. There we go. That's the amount of energy you have to put in to break the bond. That's what bond energy means. So that's 226 kilojoules. The formation, enthalpy of formation for rubidium chloride. Right? And this is in its standard state. Remember this definition. In its standard state, that's a solid. That's where you start with formation constant, or formation energy, excuse me, enthalpy of formation. And what do you start with? Well, you start with the elements in their standard states. Like that. And the amount of energy you get back when these two come together. Now, this has to be 1 mole. Stays the same. There's no, right. You can't change that one. So you have to change this one. And you only need a half of that one to get that. And that's why you have a negative enthalpy for that one. And then the last one is the electron affinity, EA, electron affinity for chlorine. So what does EA mean for chlorine? Well, that means chlorine, gas like that, plus electron yields. That's the energy that you get back from the electron falling into a single gaseous chlorine atom. Okay, that's what all of those values mean, and you need to know what each one of those means and do a better job than I did recognizing each of the abbreviations. IE is ionization energy. BE is bond energy. Delta HF is heats of formation. What does that mean? And EA is the, actually, EA was in the right place. I'll correct that later. EA was in the right place. We should have had a delta H over here for this one. And that is the electron affinity, right? Now, all of those have to go together to answer the question. What's the lattice energy? The lattice energy is defined as the rubidium ion in its gaseous state plus the chloride ion in its gaseous state yields rubidium chloride solid. Okay, what's that lattice energy? What's the energy? What's the value for the delta H here? This is a case of a pure Hess's law. You just combine these values with their delta H's, modified so that when you add them all together, you get that. And that explanation is given in the worked out problems right? So I'm not going to spend time doing it here because it's there in that document. But I did want to call your attention to these different values that have to be arranged in the correct order. Some of them have to be flipped. Some of them might have to be multiplied by a constant, either a whole number or a fraction, in order to end up with that equation. Then once you've got them ordered and the delta H's correctly modified, then you can add them together and get your answer. Okay, there was one other one that required some calculations. I think it's the one above it, 51. Let's see. Is that another case of Hess's law? I bet it is. Looks like it. Yeah. 51 is another case of Hess's law. So I'm not going to labor that one either. But we did skip 27 and 29. I do want to go back to those. Let's see. There's 29. There's 27. Let's see. 29. Use the following electronegativity values. Select from the following group the molecule that fits the given statement. This molecule contains a carbon atom with a trigonal planar geometry. Not that we need electronegativities for that one. 29. Okay, let me attack this one and see what I come up with. This is 29. Okay. So we're still on screen. Yeah, we're still in the screen. So using the values for these electronegativities, then select from the following groups the molecule that fits the given statement. Has a trigonal, the carbon has a trigonal planar geometry. It contains a carbon with a trigonal planar geometry. This has to do, the effect that the electronegativity has on the geometry is telling you, based on the localized electron model, where do the lone pairs, if there are any, where do they reside? They're going to reside on the more electronegative atoms. So if we draw these Lewis structures and we look for trigonal planar geometry, then let's just do them one at a time. We've done, actually, I think we've done all of these before, well, several of these before in previous problems. CHO. But I'll go ahead and draw them out. Okay. This carbon is going to have like that. Those three hydrogens go here. The other one is there. So that carbon has 4 groups around it, which means tetrahedral. So that doesn't satisfy. That's not trigonal planar. That's tetrahedral. But this one, if we take this carbon, well, actually, to do the Lewis dot structure, we've got to do all of them, right? So there's 1, 2, 4 is 8. Then we have 1, 2, 3, 4 hydrogens and 1 oxygen, which is 18. Right? So put single bonds, and then the hydrogens already have as many as they can handle. Subtract 2, 4, 6, 8, 10. 8 electrons. So we start from the outside and work our way in. Can't do anything on this one. It's already covered. 2, 4, 6, and 8. Is that right? 1, 2, 3, 4. Okay. There's 4 for hydrogen. 4 and 4 is 8 there. 6 for oxygen. 18. That's good. 2, 4, 6, 8, 10, 12. 12. Miscalculated. 6 electrons. 2, 4, 6. All right. So there's where we start from, this molecule. And to make an octet for carbon, we need to steal a couple here and make a double bond. There. Now, what about that carbon? We know this one's tetrahedral. That carbon is 1, 2, 3. 3 groups, no lone pairs. That's trigonal planar. So that one answers the question. And since E says none of these, then you can stop there. A is correct. If we went to carbon dioxide, we know carbon dioxide is linear, right? We know this carbon in chloromethane, this carbon has 4 bonds on it, so it's tetrahedral, right? 3 hydrogens and 1 chlorine. And this one is C2H6, which is C2H6, which is 2 carbons, 1, 2, 3, 4, 5, 6. 6 hydrogens. Those carbons are both tetrahedral. Right? So A is the only one that satisfies. And actually, the electronegativities, well, the electronegativities did inform the fact that oxygen was the originator or the sole proprietor of the lone pairs. Only we had to use one of the lone pairs to make a double bond in order to satisfy the octet for carbon. So to a limited extent, the electronegativities did have a bearing on the structure of the molecule. It's just that we really didn't have to know them to follow the rules and get the structure. So that was 29. And let's see, there, 27, I think. 27? Yes, 27. There we go. Use the following reaction data to calculate the HF bond energy. Okay. So what does that mean for calculating the bond energy for, let's see, 27. What's the bond energy for HF? I think that's right. How much energy is required to break that bond? So that's what we're looking for, which means it's going to be a positive value. We have to pump in the energy to break the bond. So this is a case also of using Hess's law to solve that problem with the given information. So we're given, let's see, get rid of those lines. There we go. We're given this energy, dihydrogen plus difluoride yields 2 HFs in the gaseous state. So there we have HF, right, in the gaseous state for this one, but it needs to be flipped, and we only need half of it, right? So for HF on this side, yields half of H2 and half of F2. What's the value for that one? Well, we flip the equation, so minus 542 now becomes plus 542. And we took half of it to get that. So we need half of 542, which is 2, let's see, 542. You can do it in my head. Let's see. 271 kilojoules. All right, so we got that one, and that takes care of this right here. So now we need to take care of those two. So the next one we have is H2 gas yields 2 H's. H2 gas yields 2 H's. But we only need one of these, right? Half of that one. Actually, it needs to flip. No. We only need half of this one. Right? So half of that one would give you this, which would cancel. And half of this one would give you that. But did we have to flip it? H2? No, we didn't have to flip it. So we only need half of it. So half of 432 is 216. Okay. And then the other one is fluorine, is similarly arranged. In that order. So we only need half of that. Half of 154 is 77. Add those together, and you should get 564. Okay. So that's a Hess's problem. It's a smaller Hess's problem than the last two we dealt with, and that was 27. Okay. I think I already did 52. Yeah, I did 52 already. Okay, so we're already 40, almost 50 minutes past. Actually, we are 50 minutes past. So I'm going to stop here and let you guys take a look at the others using the worked problems to help you with those. And of course, I'll have, I'll go straight to office hours right after this. And then I'll have office hours tomorrow morning if you have any other questions, and prepare you for the exam on Thursday. And then on Thursday, we'll get into our last chapter, chapter 9, and we'll look at more bonding, but a more, the accepted theory, current theory now, for the most complete explanation of how molecules bond.